In the previous lecture, I discussed the lives of stars and showed that the cores of massive stars can collapse, producing a dense neutron star and a supernova, a gargantuan explosion. But occasionally, some of the gas in the supernova might not achieve the escape velocity, and hence could fall back into the neutron star, increasing its mass and triggering collapse to an even more dense object, a black hole. It is even conceivable that the cores of some stars are so massive that they collapse directly to form a black hole, bypassing the neutron star stage entirely. Well, I showed tantalizing evidence that at least some supernovae do indeed produce black holes, but it would be great to witness the actual birth cries of these black holes, their moment of formation. Well, that's what we're going to do in this lecture. That's where we're going. In the 1960s and 70s, there were a dozen Vela spy satellites that had been launched by the US Air Force to monitor Soviet compliance with the Partial Nuclear Test Ban Treaty. And in particular, there was concern that the Soviets would test nuclear weapons on the backside of the moon and also in Earth's atmosphere. So these Vela satellites were fired up to high Earth orbits, and they spied, with gamma ray and X-ray detectors throughout the skies, searching for these putative violations of the Nuclear Test Ban Treaty. Well, the Vela satellites could detect gamma rays from the nuclear blasts of bombs. And gamma rays are one form of electromagnetic radiation. They're an extremely short wavelength form, high energy photons. So here you can see that the electromagnetic spectrum spans a very, very broad range of wavelengths, going from radio waves, which are very, very long, to microwaves, which are shorter, then infrared, then visible light, which is the light that we see, then the ultraviolet rays that can burn the skin, then to X-rays, which are used in doctors' offices to get X-rays of your skeleton, and finally gamma rays, which are the shortest wavelength of all, about the size of an atomic nucleus. And there's really no limit to how short gamma rays can be. The shortest gamma rays are still gamma rays. The longest radio waves are still radio waves. This is just the broad set of classifications that we have. So the gamma ray detectors on the Vela satellites could detect these gamma rays, which are produced by the decay of radioactive nuclei in nuclear blasts. Well, the Vela satellites only detected one probable secret nuclear bomb test, and it wasn't even really by the Soviets. More interesting, however, was that they found intense, short bursts of gamma rays from seemingly random places in the sky, and these lasted just a few seconds each. Now, initially, the people who discovered these things kept them a secret. It was classified because these might have been nuclear tests. But pretty quickly it was determined that they didn't have the properties of nuclear bomb tests. The scientists at Los Alamos National Laboratories, who studied these gamma ray bursts, announced in 1973 their discovery and said that they are of cosmic origin. They're not nuclear blasts made by humans. So looking out at the sky, it turns out that roughly once per day you can see one of these blasts, a short, intense burst of gamma rays coming from some seemingly random locations in the sky. And these bursts show a very incredible variety of light curves, that is, brightness of the gamma rays versus time. They all look different. In fact, the joke is that when you've seen one gamma ray burst, you've seen one gamma ray burst, because they all look different. Look at them here. You look at the brightness on the vertical axis versus time on the horizontal axis, and you can see that, in fact, some are very spiky. They go up and down very rapidly in brightness. Other ones go up rapidly and that kind of decay more smoothly. There's just a great variety of shapes. And although there is this great variety, there seems to be two general classes, the short duration gamma ray bursts lasting fewer than 2 seconds, and the long duration gamma ray bursts lasting longer than 2 seconds. And in this diagram, you can see examples of short duration GRBs and long duration GRBs. Now, the distribution of gamma ray bursts in the sky potentially provides a clue to their location, power, and physical nature. If you look at a map of the Earth in a projection of this sort, this is known as an equal area projection, where different areas on this map represent equal areas on the Earth of actual land surface area. And if you look at the sky in this way, you can see our Milky Way galaxy being this flat disk with a bulge in the central region. In the middle of that bulge, there's the nucleus, where I'll discuss a supermassive black hole later on. But anyway, this is sort of the whole sky. And when you look at the Vela gamma ray bursts that were discovered, about 70 of them, it looked like they were pretty uniformly distributed over this oval. In other words, there was no obvious concentration toward the plane of our Milky Way galaxy or the plane of our solar system or anything like that. They looked pretty uniform. But really, there were only 70 GRBs, and so we couldn't really tell how uniform this distribution really was. So the physical models for gamma ray bursts were not well constrained. We couldn't really tell whether they're in the galaxy. They looked like they are not, but who knows? Anyway, so it turns out the physical models were unconstrained, and in the 2 decades following the 1973 announcement of the discovery of gamma ray bursts, over 100 hypotheses were formed as to what they really could be. You know, matter-antimatter collisions, comets hitting neutron stars, exploding stars, black holes crashing into planets, all sorts of things. It was just an incredible variety. It was a field day for the theoretical astrophysicists. Well, in the 1990s, a lot of progress was made with NASA's Compton Gamma Ray Observatory. And here you can see an image of the Gamma Ray Observatory. In particular, it had an instrument, BATSI, the Burst and Transient Source Experiment, which was hugely successful. There were 8 little units on the corners of GRO, and they could monitor essentially the whole sky. And they found lots and lots and lots of gamma ray bursts, thousands of them. And they found, in fact, that on a map of this sort, the bursts really were distributed pretty darn uniformly. There was clearly no concentration toward the plane of the Milky Way or of our solar system or anything like that. They seemed to be an all-sky uniform distribution, unlike our Milky Way. There was also no clear concentration toward nearby galaxies like the Andromeda Galaxy, so they clearly weren't concentrated in the Andromeda Galaxy. This very uniform distribution suggested that most gamma ray bursts originate in galaxies billions of light years away. They're very rare events, and so there are few in nearby galaxies because there are not many nearby galaxies. Now, if this is correct, if they're really very, very distant objects, and yet we can see them, then they must be among the most powerful explosions in the universe because they're really far away, yet you can see them. Well, BATSI and other instruments could only tell very roughly where in the sky any particular GRB occurred. The uncertainties were of order 5 degrees. You could sort of look and say, oh, there was one sort of over there, but you couldn't pinpoint it. And within such a large, uncertain region, there would be lots and lots of stars. And so it was difficult to know what was the actual optical or radio counterpart to that gamma ray burst. That meant that they were difficult to study. I mean, suppose you have very poor vision and you see a flash of light coming generally from some direction, but not enough information to identify precisely where that flash of light came from. That's really frustrating because you can't get any additional information about that flash of light. Looking out at the sky, there are lots and lots of stars, and here you can see sort of the size of the full moon. Well, the BATSI error circles were many, many times the size of the full moon. And in a small region, like in the optical field of view of a telescope, there might be something like 10,000 galaxies if you take a long enough exposure. So over the entire circle of uncertainty of a BATSI burst, there might be, 1 million galaxies or something like that. You don't know which one is the one that produced the gamma ray burst. So for a while, the name of the game in gamma ray burst science was localization, localization, localization. That was all that was important, kind of like location, location, location in real estate. All right, well, a huge breakthrough in research on GRBs occurred when their afterglows at other wavelengths like X-ray, optical, radio were finally found. Then we could pinpoint them, study them throughout the electromagnetic spectrum, and learn much, much more. The Beppo-SAXS satellite made a huge breakthrough in that it imaged the afterglows at X-ray wavelengths. Here's the X-ray afterglow of a gamma ray burst, and you can tell quite precisely where it is. And then radio telescopes could point at the same location and see if they detect it at radio wavelengths. And optical telescopes, like the twin Keck 10-meter telescopes in Hawaii, could look at that location and see what they might find at that location. And indeed, what astronomers found was that coincident with the X-ray location, there would often be an optical afterglow. Here you see one at the left, and then a short time later, it has faded. The arrow is pointing to a very, very faint object, but for a while, it was much brighter. The Hubble Space Telescope also looked at the positions of the X-ray afterglows, and it too found optical and ultraviolet and infrared counterparts to these gamma ray bursts. Well, when the light from the position at which the gamma ray burst occurred was passed through a prism producing a spectrum, people saw that really this was galaxy light full of stars. So gamma ray bursts were occurring in galaxies. Little fuzzy blobs at the positions of gamma ray bursts looked like galaxies, and the spectrum confirmed that they are galaxies. But more importantly, the galaxies were definitely very, very far away. Because when you look at a spectrum like this, what they found was that the spectrum was shifted toward longer or redder wavelengths. This is known as the redshift, okay? Now, this is not a course on cosmology, but you should know that the universe is expanding. When we look at other galaxies, we can see them moving away from us, and the more distant ones are moving faster than the nearby ones. We know this because the spectra of more distant galaxies are more redshifted than the spectra of the nearby ones, and this means that they're expanding away from us faster. So here's a little demo of a one-dimensional universe where the galaxies are the ping pong balls. If I stretch the rubber tube, if I expand the universe, then you can see that from the perspective of this orange ping pong ball, all the others are moving away, and the more distant a galaxy is, the faster it moves away from the orange one, because there was more space between it and the orange one, and every bit of space expands. So you have this naturally occurring phenomenon where the greater the distance, the greater the speed of expansion. And it doesn't imply that we live in the center of the universe. Any ping pong ball that you happen to be on would see the same thing. The more distant ping pong balls move away faster than the nearby ones. So from the recession velocity, which is given by the redshift, you could determine the distance. And it was found that these objects are in distant galaxies. They're moving away really quickly. Now, one object in particular was so bright that it could have been seen with a pair of binoculars, yet it was 10 billion light years away. So it was clearly associated with a very distant galaxy, 10 billion light years away, yet you could see it with a pair of binoculars. How great is that? This galaxy shown here is a kind of a weird-looking galaxy. It's got lots of massive stars forming in it, suggesting that gamma ray bursts might be associated with massive stars. Well, this very distant, bright object even made the Drudge Report, which announced biggest bang in the universe recorded, like the light of a million galaxies. This is not the kind of thing that usually appears in the Drudge Report, but hey, it was big news. Now, on the 19th of March of 2008, an even more powerful gamma ray burst was discovered. It was 7.5 billion light years away, over halfway to the edge of the visible universe, yet in fact it could be seen on a dark, moonless night with the unaided eye. Now, no one saw it, no one was looking at the right place, but had they been looking at the right place, they would have seen it with the unaided eye, yet it was 7.5 billion light years away. Wow! If it had been at a distance of 6,000 light years instead of 7.5 billion light years, it would have been as bright as the daytime sun. But the sun is only 8 light minutes away, not 6,000 light years away. And here you can see it at optical wavelengths. There it is, and then it fades. It rapidly fades with time. And in fact, these data were taken by a Polish team using a small telescope in Chile at Las Campanas Observatory. It monitors about 1/12 of the sky at a time, so it's called the Pie of the Sky project. And here's the team celebrating their discovery of the optical afterglow with a bottle of champagne. Now, my robotic telescope didn't quite catch this thing at its peak. It was busy looking at another gamma ray burst at the time, and so it was only about 20 minutes later that it turned to this one that was just going off. That's unfortunate, but that's the way it goes. We did catch the decaying light curve after the first 20 minutes or so and got a really great set of data, but we missed the naked eye visibility peak. It's the big one that got away, so to speak. Oh well, you win some and you lose some. Now, the only kind of gamma ray bursts for which optical counterparts had been found for a long time were the so-called long duration gamma ray bursts, those that last more than 2 seconds. And from these data and other data, we actually could tell that it's not that the gamma ray bursts emit light uniformly in all directions. No, instead, gamma ray bursts appear to concentrate their light in a narrow beam, maybe a few degrees wide or 10 degrees wide, something like that. So if you're looking along the beam, you see it. But if you're looking away from the beam, then you won't see it at all, or it might be really, really faint. So what happened was astronomers developed a model, so-called the fireball model, where they said a jet of very rapidly moving particles, relativistically moving particles, is zooming out along a particular direction at 99% of the speed of light. And then those particles collide with other particles, both within the jet. For example, they might be zooming out at different speeds, so there could be internal collisions producing light. Or the particles can collide with the so-called interstellar medium, the gas surrounding the gamma ray burst, and those collisions produce even more light. So the gamma ray burst and the optical afterglow and the radio afterglow and the X-rays and so on come from these bursts of particles colliding internally within the jet and also with the interstellar medium surrounding the object. Okay? And if you were looking from some other direction, you wouldn't see much at all. Now, it was also found that these long-duration gamma ray bursts are often in galaxies that are actively forming many massive stars. I already showed you one example. Here it is again. This is a weird-looking galaxy, kind of irregular. It's got lots of massive stars forming, and they've been forming for the past, perhaps 100 million years. Massive stars don't last very long, so this fact that these galaxies are forming lots of massive stars suggests that the gamma ray bursts are associated with massive stars because where massive stars form, massive stars die. They just don't have much time to move to other locations. So this suggested that gamma ray bursts are associated with stars that don't live a long time. Well, some might explode as supernovae. We know that some supernovae come from massive stars whose core collapses and the rest of the stuff goes bang. So maybe gamma ray bursts are some special kind of a supernova. Maybe it's the kind of supernova that produces a beam of relativistically moving particles that pummels its way through the star, emerging out in some direction. And if we look along that direction, we see the gamma ray burst. If we look perpendicular to that direction, we see a more or less normal-looking supernova. All right? This was the so-called collapsar model, and it was developed largely by Stan Woosley at the University of California, Santa Cruz. Here you can see an artist's impression of a very massive star near the end of its life. And it's got these winds blowing away the outer atmosphere of the star. But in an animation where we'll look in the core of the star, we'll see that the core collapses, forms a jet, and that jet pummels out through the star. Let's look at that. So let's zoom in to the interior of this massive star. It's a rotating star. It's near the end of its life. The core is collapsing, forms a jet along the rotation axis where particles can escape easily. That jet pummels its way through the star, emerges from the surface, produces two oppositely directed beams, and if you are along the line of sight toward one of the two beams, you see a very bright gamma ray burst lasting for only a few seconds. That's the model. And in fact, here's an artist's impression of particularly colorful one of one of these gamma ray burst jets interacting with the interstellar medium, producing, if you're looking directly onto it, a very, very bright glow. Well, why should there be this powerful jet? Well, the massive star's core may collapse directly to a black hole releasing even more gravitational energy than the collapse to a neutron star. And if that energy can be channeled into particles, making them move fast, it's reasonable that the particles will escape along the rotation axis of this rotating star, because along the rotation axis, there's less material impeding its progress. So there's a lot of energy trying to get out, gets out along the jet that goes along the rotation axis. Gamma ray bursts may be the birth cries of black holes. What's left over is a black hole, a giant curvature of space and time. Not that we've ever seen one yet directly being produced by a gamma ray burst. We've not seen the black hole, but we think that one may well be present after the gamma ray burst has gone off. So given that at least some, and perhaps most, GRBs are associated with the birth of black holes, and that the cosmic nature of GRBs was discovered by scientists at the Los Alamos National Laboratory in New Mexico, it's perhaps appropriate that in Los Alamos there's a road called Black Hole Way. And here's a sign showing the road, Black Hole Way, kind of cool. I like pictures of signs. And near it, there's this military surplus store called Black Hole, where they sell all this, military junk, basically. I just love this kind of stuff. All right, well, suppose you've got this rapid rotation and you've got this high-speed jet of particles emerging along the axis of rotation, as shown here. It can pummel its way through the star if it is sufficiently powerful and energetic. Here you see it blasting through the star on its way out to the surface. But the more stuff it has to go through, the more energy it loses along the way. So you'd like the star to be pretty clear of material along the axis of rotation. If you have a star that looks like this during the moment of collapse, when there's not much material along the axis, it's more likely that that jet will get out. Here's another one where the jet can get out pretty easily. That's not the case if you've got a lot of star stuff in the way. So there's a demo I like to do where I've got a yogurt container, and the yogurt container doesn't allow yogurt to escape along the sides, just like the equatorial parts of the collapsing star have a lot of gas and don't let particles escape. But along the axis of the collapsing star, material is less dense and it can escape. In a similar way, along the axis of this yogurt container, there's not much material, so stuff can escape. When I drop this yogurt container, you'll see the yogurt go squirting out like a volcano in the generally vertical direction, not in the horizontal direction where its flow is impeded quite naturally. All right, so I can drop it and you can watch it do it. Boom, and it goes like that, just flying up into the sky. So that's the idea. This really wakes up my students at Cal. Well, the kinds of stars that are most likely to have this occur are the ones that don't have much hydrogen envelope to begin with. So most supernovae that come from massive stars have a thick hydrogen envelope, the so-called type 2 supernovae, but some don't have a hydrogen envelope. Those are called type 1b, and others don't even have a helium envelope. Those are called type 1c. Stars can lose their outer envelopes of gases through winds of their own near the end of their lives, as in the case of this one here, or through a process of transfer of material to a gravitationally bound companion. So you can see an artist's impression of a star transferring its outer envelope of gas to a companion. So if you have such a stripped envelope supernova go off, and it's highly rotating, not only do you have a natural axis of rotation along which stuff can escape, but you don't have as much material through which the jet has to escape because a lot of the material has already been gotten rid of by one way or another. So these are the theoretical collapsar models of gamma ray bursts. Some stars explode and are visible as supernovae, but in other collapsar models, you could, in principle, have a star collapsing all the way to a black hole, not producing a successful supernova. So you'd get a jet, but you wouldn't get a bright, visible explosion of a supernova. So the prediction is that at least some gamma ray bursts should be associated with the so-called stripped envelope supernovae, but not necessarily all gamma ray bursts. Some might directly collapse to a black hole with no associated supernova explosion. Well, in 1998, a gamma ray burst was found that was coincident with a supernova that became brighter and fainter in the following weeks. So this supernova was spatially and temporally coincident with the gamma ray burst. But some astronomers doubted that this was a real association because this was a kind of a puny gamma ray burst. It wasn't a really full-fledged one. But I thought it was a real association because the supernova looked kind of weird. It looked more energetic than a typical supernova. That supernova was a particular kind, this type 1c, highly stripped, but in its particular case, there was evidence that even much of the carbon and oxygen layer had been stripped away from the star prior to its explosion. So it was a really highly stripped star. Well, in 2003, another gamma ray burst occurred that was also later found to be associated with a supernova. And this was a more typical brightness gamma ray burst. This was a full-fledged gamma ray burst that was powerful and not some wimpy little thing that might, not have even been called by a gamma ray burst by some astronomers. Everyone agreed that GRB 030329 was indeed a gamma ray burst, and it was associated with a highly stripped envelope supernova. Okay? On the other hand, we know of some long-duration GRBs that have no clear supernova optical counterpart. So perhaps those are the ones where the star collapsed directly to a black hole and did not have a successful supernova explosion, as opposed to those that collapse to a black hole and do have a successful supernova explosion. Well, what about short-duration gamma ray bursts? I haven't said much about them yet. We didn't know much about them for a long time. But in 2004, a satellite called SWIFT was launched by NASA, and it could pinpoint the locations of gamma ray bursts very quickly and very accurately. There was the BAT, the Burst and Transient Detector, and then an X-ray telescope and a UV optical telescope on the same spacecraft that could take pictures at the location of the gamma ray burst and see X-ray and optical counterparts. So SWIFT would detect a gamma ray burst and quickly swing over so that its optical, UV, and X-ray telescopes could look at it. And what was found was that some of these short-duration gamma ray bursts are associated with galaxies having mostly old stars, not spiral galaxies or irregular galaxies having lots of massive young stars like the long-duration gamma ray bursts, but rather old stars. Here's an elliptical galaxy with mostly old stars. And the gamma ray burst occurred somewhere in that little red circle. And in that red circle, there don't appear to be any young massive stars, only old stars. So probably the short gamma ray bursts are not the collapse of massive stars. They're probably something else. And in fact, what we think they are is two neutron stars merging together, perhaps to form a black hole. If you have two neutron stars that are sufficiently close together, they can merge. They merge as a result of the release of gravitational waves. I'll describe that in Lecture 7. But when they merge, they can turn into a black hole and produce a pair of oppositely directed beams. Here's a NASA animation where they show the artist's rendition of this process. Two neutron stars are sufficiently close together that the release of gravitational waves exerts kind of a frictional force. They come together, they merge, perhaps into a black hole, and they produce two oppositely directed jets. Blam! Like that. We think that pairs of neutron stars that are merging might form a black hole and a short-duration gamma ray burst while they do so. There's also the possibility that a neutron star can merge with a black hole, producing a pair of oppositely directed jets. You can see that the neutron star gets torn apart, and then wham, it gets swallowed by the black hole, producing these jets. So in the case of two neutron stars merging together, you have the formation of a black hole. In the case of a neutron star being eaten by the black hole, you have the growth of a black hole. Either way, short-duration gamma ray bursts appear to be associated with the birth and growth of black holes. So, we expect stellar mass black holes to exist. The gamma ray bursts provide pretty good evidence for this. But the evidence from the gamma ray bursts themselves is circumstantial. We have not yet found direct evidence for a black hole at the location of a gamma ray burst, in part because black holes are so hard to see. So can we actually find the black holes themselves? I'll discuss this in the next lecture.